sorry, Professor Singh gave a wonderful history of holography, and certainly I respect him a lot. He is certainly one person I have looked up to for many years, as I said, over the decades. And certainly, of course, he being more advanced in age than me, he has come into contact with even more people in the area of holography and optics in general. As he was saying, he had the very good fortune to interact with Dennis Gabor. Excellent. So I didn't have that opportunity. So I learned a lot about his own experiences just by listening to him speak. I mean, I've spoken with him before, but every time you speak with a person of that stature, you come to know more about the person. So let's start. I mean, I didn't write the dynamic holography, but dynamic holography, of course, is part of this, course. I mean, the course content is written right there, digital and dynamic holography with applications. But one of the applications, of course, of digital holography is 3D imaging. So we'll talk about that. We'll also talk about uses of dynamic holography in 3D imaging and so on. 3D imaging is certainly the thing of, I would say, like fashion these days. I mean, everyone talks about 3D imaging. There is a Microsoft HoloLens. There's all kinds of other virtual reality, artificial reality, all kinds of stuff. Immersive reality. So, for instance, this picture is actually a 3D experience of Van Gogh. Okay, Van Gogh? He's the artist, right? So now, olden times, what used to happen? You would go to the museum and then see his works, right? I mean, so that's the typical mode of operandi. Nowadays, people want, younger generation, younger folks, if you want to interest them in, classical paintings and so on, you need to add some other dimension to it, literally, which is the third dimension, which is the immersive nature. So this traveling exhibition is actually going around the world. So I went actually maybe 3 months ago with my niece to Cincinnati, where they had this so-called immersive experience. So you just sit down in this room and really all the paintings float by you. Okay, they change. And also you can wear the HoloLens, the 3D Microsoft glasses, and you can actually, judge the depth, of course, and also using hand gestures, simple hand gestures, you can make the, thing move closer to you, further than you, and so on. So that would be, I would say, the new wave of art appreciation. And you need to actually step up to that because things are happening quickly. And the one other point I want to stress right from the beginning of this course, it's not just only computer programming. So just learning software is not going to work. You have to develop some hard products. And this is a major thing I always say whenever I talk to my colleagues here. India needs to have hard products, not only software. You need to be identifying a product which the world will know you are known for. I mean, Samsung, for instance, has their cell phone, or they have their Hyundai and the Kia. Everyone in the world knows that there is this product. We need to have something like that. Okay, software only is not the answer. So whenever you are thinking of any of this, think of an application in mind, think of some product you can make and you can sell. And I'll give you a very simple example. You go to an SPIE meeting, Photonics West as an example, which has so many exhibitors from around the world. Indian stalls, you'll see two or three. Chinese stalls, you'll see 2 rows of them. Why should that be the case? If we want to say that we are as good or better than China, we should prove it on the level playing field. We should make products. And those products should not be shabby. Should be products that you can make by the millions, and everyone should be able to use them. So I will reiterate this throughout this course. That's what the future generation should do here. All right? Okay, good. So let's move on. So first of all, I wanted to introduce you to where I am. Because again, this part is history, but it is actually a good part of history. Just like you heard the history of holography from Professor Singh, I'm going to talk a little bit of the town that I am in. And I'm certainly proud to say that I live in this town because this town called Dayton, Ohio, is actually known as the birthplace of aviation. So that is a place where the Wright brothers, okay, again, see, they built something, okay, they just didn't write down theory and equation. It doesn't work, okay, you have to build something. They were just bicycle mechanics, and they built the first airplane. They flew it, in this first thing, they flew it in this area. It's called Huffman Field. It's very close to the city where I stay. I mean, it's just a neighborhood. And then they took the whole contraption to North Carolina, where they flew it in the winter. So there started the aviation, and Dayton has been known as, a hub of aviation. And for that reason, as you see, there's a big Air Force base there. It's called the Wright-Patterson Air Force Base. Okay, so Wright is after the Wright brothers. Patterson, another very well-known discoverer and inventor. So Wright-Patterson Air Force Base is based in Dayton. They do about, well, I would say about $2 to $3 billion of research every year. So they are the research branch, scientific research branch, big branch of the Air Force. They just don't fly, fighter planes and bombers. No, they develop new products. Like these other ones that Professor Singh was talking about, all this classified work, quote unquote classified. Many of those work are done here. I mean, they are not really all classified. I mean, I go and work there, and they are kind of like a, basic research. Okay, so basic research, lots of basic research is really done at the airport. And they have excellent laboratory facilities where our students go, as a matter of fact. But plus, this museum is certainly something very worthwhile to see. It's number one, it's free. Number two, you can spend a whole day seeing the entire, evolution of aviation. So anyone who comes there, I would recommend you to go there. So geographically, this is the map of Ohio. Up north here is, of course, Michigan up here. That's where, holography, off-axis holography was discovered. Not very far. It's really literally 3 hours from my place because it's at the University of Michigan, Ann Arbor. And incidentally, I do not know, I mean, you probably will not know, American football is a big thing in America, of course, and then American football rivalries are also big. So there's a big rivalry between University of Michigan and the Ohio State University, very close to where I am in Columbus. So anyway, so this is the geography of my place, and so we are right here in between, as you see, Columbus and Cincinnati. So it's a convenient location. This is a view from from my office actually on a full moon night. This is actually Catholic University, University of Dayton. This is like the downtown Dayton. Downtown Dayton actually has 5 small rivers that meet in the downtown. 3 come in and 2 go out. And they actually have a nice laser show on the river in the summers. Again, lasers and, beam deflectors to move the lasers around to the middle. A lot of people have come to Dayton, these guys, okay? So Obama came one time along with the British Prime Minister to see a basketball game. Dayton is known for basketball as well. Wright brothers, and as I said, the birth of the aerospace industry is in Dayton. Charles Kettering. Who is Charles Kettering? Well, the guy who invented the spark plug in the automobile. So that's why automobile industry is very big in Ohio and also in Michigan, a little bit up north. So they were the first who actually invented the ignition, self-ignition, and self-starter. And that became a part of General Motors. So Dayton actually is known as a birthplace of also not only aviation, but also inventors. So there's a whole bunch of inventors. This guy, okay, not that favorite, okay, he invented the pop-top can, okay, fine. All the Coke machines, you have the pop-top. But the other one, NCR cash register, the NCR, all the ATM. These ATM machines were all built in Dayton previously. Till, of course, America outsources, right? Because things are becoming more expensive to build. So, of course, they outsource to India, one place, to Romania, and to China. But all the cash machines, they are made by NCR. That's where it started out from. The other well-known person there is this guy, Joe Dash. What did he do? Well, he was really the brainchild behind uncracking the German Enigma codes. You see the movie, okay? The mathematician, what's his name? Yeah, so he did up to a certain point, but that did not destroy the German submarine. The first German submarine was destroyed by the uncoding of the code by this guy, Joe Dash, who was a graduate from our department, actually. So he started working in NCR, and in fact, I mean, I wrote a little biography on him because he was from our department, electrical engineering, and also he really had to live a very miserable life because he never could tell others what he actually did. He was barred from telling others, and he really died in sorrow. Till all of this stuff was brought out really by his daughter. Okay, his daughter was talking with her son, going to school to talk about grandfather
Hello, sir. Sir, we can't hear you.
unnecessarily so many more connections than required.
If you had a, HDMI,
Please ensure that tomorrow that
if you have a HDMI cable, that'll be fine. Okay, hopefully we move. Okay, thank you. Let's see how long it stays. Is that okay there? Okay. So as I was saying, this is part of one of my labs. So I'll talk more about what we do, but this, oh, I think there's probably this pen, right? Okay. So one of my students is here. Her name is Saleha Kisi. So she is a student funded by the Saudi government to come and do her PhD. She's actually working on, guess what, digital volume holography. Okay, so a little bit different. Okay, you heard about volume holograms, you heard about digital holograms. He is doing digital volume holograms. So I'll talk to you about that. So how you can record a digital transmission hologram and then change it numerically to a digital volume hologram. What's the advantage of that? As Professor Singh was saying, much better wavelength selectivity. So that's what we will be seeing too later on. All right. So we also have collaboration with Huazhong University of Science and Technology, and that is in Wuhan. You've all heard of Wuhan, right? But it is one of the best schools in optics. It's the third best schools in optics in China. And really, again, I have been going there every year, except during, of course, the COVID time. The last time I went was 2019. Wuhan is also called the Optics Valley. And Wuhan also hosts a tennis tournament, like the ATP tennis tournament, like you have here in Chennai. Wuhan itself holds a tennis tournament. All the top players in the world go there, and they're all funded, by these optics companies. And there are at least 100 optics companies there. I have personally seen them. So that's why I'm saying you need to make products. Their graduates, a lot of their graduates go work for defense, and the Chinese government, as certainly is eager to learn about technologies from all around the world. Okay, but that's one part. But there is a whole bunch of these graduates from the universities who go and work in those companies. As I said, there are 100 to 200 optics companies there in Wuhan, and they are making optics products, which you yourself, I've heard, you can buy. I mean, they're cheaper, as you certainly, than U.S. products. They may not last as long, okay, but so be it. I mean, they will last long enough, for you to do something with them, and they're very reliable. Anyway, so our university also offers, as you can see, this is just a pitch for our university and our department. We do offer assistantships. A lot of government and industry work goes on there. We have at least 25 specialized research labs in optics, and we also give short courses. We also do short courses there in the summer, different areas. Digital holography was one. I have not done it recently just because I was busy with other stuff and so on. And also another thing we do, we emphasize is hands-on lab and optics courses. Even at the master's level, there are three graduate labs. Everyone has to go and work there, at least have some experience. Okay, good. So let me talk about a little bit of my history. And there's a reason why I'm doing this, because as I said, you need to use concepts from one area, try to apply it to another area. That's how you advance in research. So let me give you my background. I'm old, as you can see, okay, 1978. It's way before you guys were born, maybe when your dads were born, right? So I was an undergraduate student at IIT Kharagpur, right? So one of our professors, who actually many others of my generation will know, his name is Dr. N.B. Chakravarti. He was very well known in solid state devices. And he taught us the solid state course. He had graduated, he had got his PhD degree from England, from Loughborough University. It was a very good school. So he always would encourage us to talk on hot topics, okay? And he would drive us crazy, talk about hot topics, talk about hot topics. Okay, so along with me, another friend of mine chose this topic of acousto-optics. Remember Professor Singh was talking about acousto-optics? That's also a grating. It's a volume grating, okay? this work on acoustic optics, a lot of work was done by who would become my advisor. His name is Adrian Carpel. And Adrian Carpel actually used to work at Zenith Radio. That's a radio company and a TV company in the United States, which has gone out of business. But they used to do a lot of research on TV and other stuff as well. So I found out that from my dorm mate that the author of this article, Adrian Carpel, who was at Zenith Radio, had recently moved as a faculty to the University of Iowa. And so I was very interested in that topic, and I read his life history as well. Very, very intelligent person. So guess what? I wrote to him an aerogram. I did not even bother to, get that time by mail the application form. So I sent him an aerogram, and that aerogram still exists in the department because that was the only guy who ever sent an aerogram as an application. So anyway, so I did get a scholarship from him, and these were the scholarships at that time, $500 a month. So anyways, when I arrived there, he asked me to work with him not on acousto-optics, but on something called solitons. I don't know if you've heard the word solitons. Solitons are waves that can propagate, well, in water originally, certainly in fibers. A lot of fiber communication systems are based on solitons these days. So he asked me to work on solitons and nonlinear waves in water. So initially I was disappointed because I came here to work on acousto-optics, but that actually opened up a lot of opportunities. So I studied acousto-optics on the side with my friend Poon, T.C. Poon, who to this day I collaborate with, and we have written books together. He also has a book on digital holography with MATLAB, a very good book. So I also worked on solitons, on waves in water, and after my master's, I started working more on experiments. I worked on experiments on water waves. So water waves I generated in a water tank. So you might be asking me, what the heck am I doing here? I'm in electrical and computer engineering, but I'm working with water waves. The principles are very similar, okay, and same principles in physics as well, okay. So using this water tank, which was really designed by me along with my advisor, Carpel, who was really a hell of an innovator, an engineer and an innovator. And I'll tell you more about him in a next slide. So I designed this one where for the first time I could see subharmonic generation in waves. Subharmonic generation in water waves is much easier to see than in optics. In optics you can see it, but it's it's a parametric interaction, but it's much more difficult in optics to do. But the physics is still the same. And the other thing also I saw on the water waves is self-refraction, which is, if anyone has heard about nonlinear optics, there is the phenomenon of self-focusing and self-defocusing. They are all very easy to see using these water waves. And we had papers those days published in, as you see, the physics of fluids. But physics of fluids or optics, um, they're really the same. The principles are really the same. So this actually helped me a lot. It helped me, encouraged me to apply concepts from one place to another. So moving on, by the way, my advisor, Adrian Carpel, he turned 90 this year in February. So I, along with some of his other colleagues, some of my other colleagues, his former students, we actually wrote an article on him, which you can find in this month's Optics and Photonics News. So this is brand new, just came out the other day. So this is him working at Zenith. Next to him is a gentleman called Robert Adler, who was his mentor at Zenith. And guess what this guy is known for? He discovered the TV remote. Okay, so he is the TV remote guy. And what is Corporal known for? Well, he is known for, ultrasound imaging. Okay, so he was the guy who first started the ultrasound imaging, along with many of his other discoveries. And again, he was a physicist, and you'll see that written in this article. I spent a lot of time, we all spent a lot of time writing this. He was a physicist, but he was an engineer, and he could build products. And when he was in our lab, he could take a TV apart and put it together. Okay, and I was so impressed I bought a Zenith color TV. Okay, those days color TVs were hard to find. I bought a, like a 32-inch color TV for $500. Zenith color TV, that's very good. But feel free to read this up. It talks about his interest in certainly acousto-optics, which is volume grating. So his main contribution was in acousto-optics, making products from acousto-optics after it was first, you know, predicted by Brillouin in 1922. And in fact, this marks the 100th year of the first paper on acousto-optics by Brillouin. And this article also was written to commemorate his 90th birthday. And he was the first who made acousto-optics into products. Okay, so he has more than 36 patents, actually. And his boss, this guy at Zenith, Robert Adler, has more than 100 patents. Thomas Edison is the guy who has the most number of patents. That was about 200. So they are all in that range. Okay, so feel free to read this up. But the other thing I wanted to mention, so he also has, as you can see, articles on holography. He has personally met, of course, Gabor. And this article, a little review of Gabor frequency, time, and memory came out in Applied Optics in 1982. And I bring this up because along with another friend of mine who was a student, he then looked at what are called nonlinear echoes. These nonlinear echoes or phase conjugation in electronic systems is the same as time reversal. Time reversal is very similar to phase reversal. And phase reversal means like phase conjugation, which Professor Singh was also talking about. Holography that you see here is really a two-step process of phase conjugation. You can do the same thing in one step if you had a nonlinear optical material. You okay with this? So I want you to get out from this course with knowing some of these details, how you can connect one topic to another topic. Okay, don't just restrict yourself like a horse going down the track. Keep your eyes open, then you can relate more. So that's why I brought these two up, and it's just coincidental that this just came out actually this month. Okay, so moving on. So then I got my first job at Syracuse University. And so there I worked on certainly solitons. And then after that, when I went to Syracuse, I don't know, many of you may not know, Syracuse was well known for electromagnetics. One of the top people there, Roger Harrington, he has a classic book called Time Harmonic Electromagnetic Fields. There are a whole bunch of other people. There is a book in undergraduate, many people follow around the world, is by Cheng, undergraduate course in electromagnetics. So he retired. Cheng retired, and I was the substitute. I as a new faculty, I joined in. So of course, I learned a lot about electromagnetics. I started how to break apart a laser and make it back to work again. Then in 1988, I went to work with Baha Saleh. Many of you have heard of his book, Saleh and Type, the big fat book on photonics. So that's when he was writing the book, and he asked me to review his chapter on acousto-optics. So if you find any issues with that chapter, I am partly to blame because I reviewed his chapter. Of course, he has gone through many editions after that. But other than that, I also worked on my first book, and that time I also learned, this transfer function for propagation. This business of transfer function for propagation was not known till that time. When I studied Fourier optics, Goodman's was of course the only book. There was no word of the transfer function for propagation. There was just a little section on the angular plane wave spectrum, and that's where it ended. So when I started at Syracuse, I thought that this is too difficult. I mean, I want to do something simpler. And, coming from electrical engineering background, as Goodman was as well. So I, went on my own, derived the transfer function of propagation, applied it to diffraction problems. And my first work was actually published in the Proceedings of IEEE, like here, this one. This was the first work on, how to derive the transfer function for propagation, which is, of course, used to this day. And later on, of course, I was certainly satisfied to see my book on sale at Stanford next to Goodman's book. And Goodman's, used to follow my book at a lower level. And then Goodman incorporated this business of transfer function to his book. So that's the history of the transfer function for propagation. Again, it's something that I learned from my advisor because we were doing what's called the split-step angular plane wave spectrum method in trying to understand, water wave propagation. And at that time, I didn't know how to get to this transfer function, so I just worked it out myself. And that should be the way you should all work. Okay, once again, okay. Think of something and try to do it in your own way. That's the best way to learn. Okay, so other things that I learned through the process was chaos. Also worked on the Z-scan. People in nonlinear optics may know about Z-scan, which is a way of measuring the nonlinearity of a material and so on and so forth. And then, one day in a lab, someone came and said, oh, there is this crystal lying around. No one knows what this thing is, so you can work with it. So it turned out it was a BSO crystal, okay? So bismuth strontium oxide. It's a reddish colored crystal. That's the time I started first looking into the world of photorefractive. So this was around 1990, 1991. So then, shortly after that, I moved to University of Alabama in Huntsville, where, much to my delight, I came into contact with a pioneer in photorefractives, Nikolai Kukhtarev, after whom the Kukhtarev equations are written. That models how dynamic holograms are stored in these photorefractive materials, and we'll look at some of them pretty soon. So that got my interest started in photorefractives. Okay. Now, as Professor Singh mentioned, photorefractive materials store holograms, okay, which are phase gratings. Okay, they could be transmission phase gratings, they could be reflection phase gratings. If you have transmission phase gratings, you can do like energy transfer between one beam and another, two-way mixing as it is called. You can also do the same thing with reflection gratings. This particular thing, again, happened very coincidentally. So there was another crystal lying around, in Huntsville. It was a potassium niobate crystal. This potassium niobate crystal is a little bit different kind than the BSO crystal, which I mentioned before. This is actually a very fast crystal, and change in the refractive index, I will go through the math later on, is proportional to the intensity of the light through the material. So one day I was playing around with it, okay, what I found is, so when I shine just light on the material, okay, in the far field, you see a small dot in the center, but after some time, the dot breaks up and makes up these 6 other dots on the side. This is what is called a hexagonal pattern. And it was, at the same time, first observed by a guy from Japan, from Tsukuba University. His name is Tokiyuki Honda. So together with Nikolai and Honda, we started working together, and we did a lot of fundamental work on this once again. And as it turns out, this is a very interesting thing, because what happens inside the material is a process called self-organization. So you don't have to do anything else to write the hologram. The beam itself, okay, from noise, okay, excites other spots. Okay, these are really small spots all the way around, and that in turn writes gratings, which couples light to different orders, and the strongest gratings survive. And those strongest surviving gratings give rise to this hexagonal pattern. And what you see as hexagonal pattern in the far field really amounts to this periodic hexagonal pattern in the near field. Now, you might have learned something, some Fourier optics, I'm sure, before, an effect called the Talbot effect. What is a Talbot effect? If you have a periodic transparency and illuminate that by a collimated laser beam, the periodic transparency in the Fresnel region during diffraction shows the same pattern repeating. So that's called self-repeating patterns, named after the guy who first found it, Talbot imaging. So that's really what is going on inside the material. So inside the material, you're really writing phase gratings. The phase gratings exist, of course, inside the material, but as they propagate, this is light. Okay, light is coupled with the matter. As they propagate, they transfer from a phase grating to an amplitude grating and back to a phase grating. And this periodic pattern goes throughout the bulk of the material. So really what I've done here is actually stored a lot of information here. You can change the amount of information by changing the orientation of the light and so on and so forth. So I'll talk more about that later on. Once again, see, these are surprising things, but then you need to stay with it and try and understand what is going on, and it, opens up a whole door of possibility. All right, moving on. So another thing that I also did, so, one time, uh, a guy from computer science came to me, and computer engineering really came to me and said, "Sir, my advisor has thrown me away." I asked why. He said, "Well, I was not progressing well." So, okay. So I'm like maybe like the savior. And so he said, "Can I do a project with you?" I said, "Oh, yes, okay, come on down." So I tried to explain to her, this business of self-organization. And I learned about, there is a common theory called swarm theory, particle theory. So by using the swarm theory, you can also explain the whole process of self-organization. So you have a wave equivalent model to explain it and a particle or corpuscular model to explain it. So both can be done. So as you see here, okay, this is really, kind of like providing information to ants, how ants actually collect food from one region and take it to another region. So you prescribe the rules for self-organization and, start out with a bunch of particles in the center. You'll see after some time, these particles are going to disperse to the circle around and then break up and then finally form the hexagonal pattern as predicted from swarm, clustering theory. Okay, the other thing we also do with digital holography, I'll talk about. This is a recent grant also we got from the Department of Homeland Security. Uh, it's a frightening phrase, right? Department of Homeland Security. But no, they have a better side too. And they're not only responsible for driving people away, they also do bring in people. Okay, the driving people away part is really, the topmost politicians. So that's how they get a bad name. But no, they also do a lot of good fundamental research. So this work over here is along with a colleague of mine at Penn State, Akhilesh Lakhia, on analysis of fingerprints. Now this is another up and coming area. Okay, why? Because if you look at your fingers, okay, the fingerprints, actually they're called finger marks these days. Because fingerprints is what you leave behind, when put your fingerprint on a piece of paper. But these are called finger marks. But if you look at that, they're really 3D, right? They're 3D. But so far, not much has been done with the third dimension, although that is also unique to a person. So how did I come across this? Once again, one day my friend Akhilesh said, "Hey, I have some fingerprints. Can you analyze using digital holography?" I said, "Oh yeah, sure, we can do it." And in fact, we could see very good 3D details. Okay, now, this also got me interested because, again, there is history involved. So then I started learning about fingerprints, okay? And the only thing I knew is, so my mom, when she went to apply for US citizenship, because I was the only child and my parents stayed with me, she went 5 times to the fingerprint office. She could not register her fingerprint. Okay, so elderly people, their fingerprints are washed away, or their finger marks are washed away. Why? Guess why? With years of cooking, all the spices and everything, they take a toll on the finger. So she became a U.S. citizen without a registered fingerprint. Department of Homeland Security is sometimes good. You see, they don't drive people away all the time. But okay, but other than that, it's also true, biologically true, children under 7 don't develop the finger marks as well. So as my friend says, if you want to steal chocolates, uh, get a child under 7 because there'll be no fingerprints left. Okay. So under 7, okay, easy to steal chocolates and stuff like that. Nothing left. But anyway, so we are doing a lot of work on the fingerprint. Besides, history of fingerprints. It was started in, guess where? My hometown of Kolkata. That's where the science of fingerprint started in the year 1908. How did it start? You can look at the history. Okay, there were two constables. You know who are constables? Under the British Raj, the police officers used to be called constables. So there was a Hindu constable and a Muslim constable. So these two guys, okay, they took it upon themselves to find some way, some kind of logical way of, kind of keeping records of crooks and criminals. So they started this business of fingerprints, which, of course, they reported to their boss. The boss was this, of course, I call him an idiot, okay, a stealer, okay, a British, boss who actually didn't acknowledge them and then took it and showed the technology to Scotland Yard and was highly recognized.
Is this the same person who happens to be the younger son of William Nixon,
Yeah, yeah,
ex-father?
yeah, same guy. Well, the Harshal guy is a top-known guy.
Yeah,
Yeah,
he's a top-known guy, but he was infamous for the whole theory of
yeah.
sun. He was thinking that the inner part of sun is cold and outer part is
Oh, is
hot.
that right?
What you see are the
Ah,
ways to the colder part.
yeah. So he's related. He's part of the Khan guys. Yeah.
And he, in fact, stopped many people from research for long time. That's why they say like something.
Well known. Yeah. So yeah. So finally, those guys are rewarded. They were given some title and money. Typically like people will give compensation. Even these days, that's how people settle things. But anyway, so that got me interested in fingerprints. So right now, we have a project from them to characterize many kinds of fingerprints. And fingerprints, the thing you want to characterize are latent fingerprints. Latent fingerprints means fingerprints that are left on these kinds of bottles and cups and saucers. And also level three. Level three is the level of the depth of the pores. If you look at the fingerprint, why do you sweat? You sweat because there are pores, and pores give out oils. Okay, that's what you register. When you put on, the finger marks on these bottles. So the pores have the same kind of pores like on your skin over here. So they have the 3D information as well, and that has not been used so far. So what we are trying to do is trying to establish a new standard for 3D finger marking or fingerprinting. This project actually has gotten some coverage in the press just because it relates to the common person, right? So I have actually appeared in some NPR interviews, National Public Radio interviews, just because people are interested and they have to set up new standards for this. So we are also working together with the forensic department, which is called the Dayton Crime Lab or Miami Valley Crime Lab. So later on, I'll talk to you a little bit about that. Are you okay with this? So you see these applications coming in. The other thing we also do are, neural network design of metallodielectric filters. This is an area of work in, as you know, in metamaterials. And so these are, tunable optical filters that we design. And once again, the design of this, so traditionally, how was the design done? Okay, these neural networks. So you feed a bunch of information. This is another issue I have. You feed a bunch of information, then you, of course, have some protocol to get the best design, right? That's how it works. It would be much better if you could, do the same design by, reducing the amount of inputs you give to, kind of train the system. So one of the things that I actually did is, the concept of dispersion relations for these structures. As it turns out, these kinds of structures, the dispersion relations for electric waves or optical waves, so these structures can be derived the same way as what you do in a quantum mechanics in the simple, crystal model. If you have a periodic lattice, you can figure out how the crystalline structure permits different Brillouin zones for, waves to propagate. The same kind of thing happens here. So if you know the dispersion relation, you can then automatically find out, what is the pass band, what is the center wavelength, the cutoffs, and so on. And if you input those into, your ANN machine, the amount of information you need is much less. So again, it's, cross topics, using concepts from one to the other. Okay, so this I don't want to go over. This is a whole bunch of my students who have been working in this area, holography and metamaterials. But some of the work actually, so one of the things I'll mention here is that, these three guys, okay, this Namatala, Ilo, and Williams, all these three were my students, okay, and after they graduated, they themselves wrote a book, Analog and Digital Holography with MATLAB. And I'll certainly encourage you to look at the book and do some of the problems. There's a lot of programs also written in the book. And this particular book was, I would say at least 50% of the work was developed in my lab. Okay, so it's like, and no one taught me digital holography, by the way. I'll tell you how I started with digital holography. So the way I started with digital holography was, okay, I'll get to that. The way I started with digital holography, similar to photorefractive, is one day I went and then, someone told me, oh, shall we apply for this small business, research initiative? They're called SBIR programs. So, okay, where do you apply? It's some project from the Army. Typically the defense gives some small amount of money to start. What was the project about? Well, the project, as you see in this book itself, project had to do with making holograms of water droplets and ice, cubes. Why? Because when, fast-moving aircraft move through the clouds that have a lot of rain, that have a lot of ice particles, they are damaged just because they're moving at a high velocity. So our job, the first job that we had, was to actually make holograms of water droplets and of surfaces that have been impacted by these water droplets from, planes that are flying at high speed. The other project that we had that again got me started on holographic interferometry and using, say, photorefractive materials as a dynamic holographic storage element was, to find out the pitch, yaw, and roll of an aircraft of a test aircraft in a wind tunnel. So we got again some kind of a grant from Air Force. So they have a big wind tunnel facility, and in fact, not one, but multiple. So our job was to actually find out, changes in attitude of model aircraft in the wind tunnel holographically by using holographic interferometry. So that's what got me actually started in the area of digital holography, holographic interferometry, and so on. Okay. And everything, as I said, is self-taught. Okay. So I had to struggle and learn. And you should do the same thing too, because that's the best way to learn, really. Sorry, okay, any questions so far? Now we'll get into more detail. Any questions on background so far that I laid out? Do you see the connection here? Do you see the connection between different topics? Okay. Don't ignore a topic just because you say, oh, it's no good. No. I mean, you can always find something interesting and apply it to, your primary area of interest. See, as you see, waterways. I mean, what has waterways got to do with this? But there is a lot of commonality between. All right? Okay, so moving on. So this one, uh, I wanted to first talk a little bit about, the path to holography. As everyone knows, of course, there is the wave theory, of light. There is, of course, the particle theory of light. And in between, there is also the polarization. And you know of all of these, right? I mean, you know that, Huygens principle defines, the wave nature of light, getting down to, of course, Young's double slit experiment, down to the Fresnel, some people call it Fresnel, but it really should be Fresnel diffraction formula. And of course, good old Maxwell, after whom everything is modeled, and then Hertz, okay? And on this side, of course, there is the corpuscular branch, okay? There is, of course, Newton, then there is Kirchhoff, there is Planck, and of course, Einstein as well. And then here in the middle are the guys who actually invented polarization, So there is Malus. You've all heard about Malus law. Okay. And then there's Michelson, and Heisenberg, Dirac, Schrödinger, and so on and so forth. So these are the three kind of arms, I would like to say, of the treatment of light, and every one of them is, of course, important. Um, Certainly, the most, I would say, topmost discovery in this field was, of course, by Maxwell, because without his equations, we couldn't do anything. By the way, this summer I went to visit Edinburgh. That is the birthplace of Maxwell. Okay, so this is Maxwell's house. Okay, typically, in U.S. there is a coffee brand called Maxwell House, but this is the real Maxwell's house. Its address is very interesting. It's 14 India Street, and there is a reason for that. The reason is because Edinburgh used to do a lot of business with India at that time, so that street was named India Street. It's a very small house. His parents were, his dad was a lawyer. His mom was, of some blue blood. And they had this kid. I had many pictures. I didn't show it. So this is a plaque in front of his front door. This plaque was put up when Albert Einstein visited Maxwell's house, really. And according to him, okay, he actually did say that one scientific epoch ended, another began with Maxwell. So Einstein himself recognized Maxwell. In fact, it is known that Einstein kept a picture of Maxwell till he died by his bedside. So Maxwell himself didn't live for too long. Okay, he had stomach ulcer. His whole family had stomach ulcer. His mom died of stomach ulcer. He died of stomach ulcer. But guess what? The amount of discoveries that he did in this short amount of time, in 39 years. Okay, I mean, we talk about Swami Vivekananda. This guy did much more than that. Okay, I mean, he did things tangible and intangible. He was also one of the first guys, okay, who actually discovered color photography, which I did not know. All right, so moving on, we'll be mainly talking in this short course about holograms made from dynamic phase. Okay, this is one thing you need to remember, because there's other kinds of phases, and I have my own, I would say, opinions about it. There is something called geometric phase and something called dynamic phase. This geometric phase, some of you may have read about it in physics. It's also called the Pancharatnam phase. He is, of course, an Indian physicist, and he discovered this way back in the early 1900s. And later on, it was just more changed a little bit by other guy, Berry. So sometimes it's called Pancharatnam Berry phase. Okay. So this is the classic experiment that shows the difference between geometric phase and dynamic phase. I don't want to get into the details just because we are not so much interested in geometric phase optical elements here. We'll be more interested in dynamic phase. But remember that geometric phase has been employed in holography as well. Okay. So, by the way, I will give you copies of all of these slides. And the reason is, I mean, I'm also, putting things together. So, like after this one, I will, send you all these slides. So, there are things that are called geometrical phase holograms. Okay. They're called holograms. Why? Because they're grating. Okay, now everyone wants to be fancy, right? I mean, if I make a grating, but I want to sell it, so I won't call it a grating. I'll call it a hologram. It will sell much better. What costs $1 will now be sold for $50. So, because the word, right? I mean, it's just like a tie, right? You put the name, Liz Claiborne, it will sell for much higher. It's made in the same factory as your other product. But anyway, so here, okay, so this is Amsterdam's train station, okay, and this is actually called the Rainbow Station, and designed by an artist. His name is Dan Rusegaard. And so this, as you can see, shows, striking colors. It changes during the times of the day and so on. But this is actually called, holographic, optical element made from geometrical phase holograms. Okay. Now, one way you can do these geometrical phase holograms is using like a liquid crystal patterning. So all you are doing here, again, making gratings. In liquid crystal, you also make gratings. But liquid crystal, you know probably typical pneumatic liquid crystals, how they behave and so on. But you can also make fluorospheric liquid crystals where the molecules rotate a certain way and so on. If you look in the details of this one, you will see that the tilts of these molecules across this grating, are, anti-symmetric. See here, they are kind of in this direction, that direction. There it's exactly the opposite. So on and so forth. So you have to arrange it in that particular form. So this kind of thing can split the light into these different orders and at a high diffraction efficiency, okay? At a very high diffraction, typically 90% diffraction efficiency. So these kinds of liquid crystal elements, okay, people also call geometrical phase holograms. But my objection to this term is that if you actually study how the light propagates through that thickness of the liquid crystal. Understood, the thickness of the liquid crystal is not much. It's of the order of 10 microns or 20 microns. That's a typical thickness, right? But if you study, and how do you study that? Well, there is a set of equations that's called the Berryman equation. Berryman was one of the first guys who, starting from Maxwell's equations, incorporated inhomogeneity as in the case of liquid crystal. So if you provided the Berryman equations the necessary conditions for optical propagation from one side of the liquid crystal to the other, you would see that the light would be broken up into the respective diffracted orders as predicted here. So that what I mean to say is it's really propagation once again. It's propagation through a inhomogeneous medium. Okay, it's propagation through an inhomogeneous medium that is causing the diffraction of light into different orders. But if you did not know that, if you did not know there's a liquid crystal element in between, then you would say, okay, between the input and the output, the light has been broken up into three different orders. Therefore, this is an effect of geometric phase. That's what people say. But according to me, and I may be wrong, but I think this way. Yes, you know, as Professor Singh was saying, how thin is thin, how fat is all relative. So if you just think of this thin substance and you do not know what's going on inside the material, you only see on one side and the other side, you say, oh yeah, this is magic. Okay, this is like my geometric field. But if you went down and studied the mechanism of why the light is split up, I think you can find that out from just the laws of propagation. But then it's propagation in an inhomogeneous material. Are you okay with this concept here? Anyways, regardless, we are not going to talk too much about geometric phase holograms. How are you doing with the time? I have no idea of time. 4:06. Okay, let's go on for a little bit and then we'll, ask you to do some problem. Okay. So are you okay with this? Geometric phase? Okay, so getting back to propagational phase and propagation of light, some of the things that we really need to be absolutely clear about are Fourier transforms. Okay, I'm sure all of you know Fourier transforms. I will just go over it once again because some of the things I'll ask you to request you. I shouldn't say ask you, request you to do. Okay, my PhD advisor, by the way, Corpo, whenever we had to see him, okay, whenever we had to see him, guess what he would come and tell. He would say, oh, would you like to see me? He was that polite. Okay, so I try to do the same with my students as well. So same thing, I would like to request you. Request doesn't mean that, it's another way of saying you better do it. Yeah. But yeah, request you to do is a better way to say. Because every one of you are professionals and we are like colleagues over here. So one of the things I will follow in this class is the electrical engineering convention. Guess why? Because my degrees are in electrical engineering. And engineering convention for traveling wave, for instance, that's a little bit different than the physics convention. First thing, I don't know why, of course, engineers use J for square root of -1, physicists use I. But if you want to be consistent, in most cases, if you put J equals -I, it works, except in Goodman's book. Okay, Goodman's book, it doesn't work. Goodman writes J, but he uses the physics convention for traveling. So this is another thing you need to be, able to be in step with all kinds of different notation. I'm sure, you are more experienced than the students I deal with in my first class on Fourier optics. So their first complaint is, which book are you using and what notation you're going to follow? Well, there is no standard notation. I tell them, you can reach heaven in, 1,000 different ways. There are 50, 100 different religions. You go to the same place finally. So better get used to it from now. So what is I is also the same as J. You need to understand the differences. Some people write F for frequency. I write omega for frequency because that's what I was used to. But you need to be able to make the transition. You okay with that? Everyone okay with that? Okay. I mean, the first time when I was taught a course in, like signals and systems, of course, in IIT Kharagpur, was by a guy whose book is actually well known all around the world. His name is B.P. Lathi. So it's a communication system, a standard communication system. So these notations are from there. And I like the notations, so I'm not changing the notation. Okay, so in his case, okay, the one-dimensional Fourier transform pair in time is given in this way. Okay, this is his definition, which still is true. Okay, the forward transform has a e to the minus j omega t. Reverse transform has e to the plus j omega t. And this ensures that the forward and backward transforms are compatible with each other. And there's also a factor of 1 over 2 pi because if you take a forward transform followed by inverse transform, you should get back the same function. So in a similar way, in my case, I will always define the one-dimensional Fourier transform in space, just like these integrals, except here for the forward integral, there was e to the minus j omega t. In my case, for the forward integral, I write e to the plus j k sub x and then x. You okay here? So instead of minus there, I put plus, and I'll tell you the reason for that. Okay, and then k sub x, okay, that's the equivalent of omega. Omega is the angular frequency, of course. The units are radians per second. The k sub x is the spatial frequency. The units of spatial frequency is radians per meter, right? You okay with that? Okay, and the inverse transform similarly, because this forward transform has a plus sign, inverse transform has a minus sign. So that is a Fourier transform pair. Now, the reason why I inverted the signs, okay, is because of the following fact. You see, if I had a function f of x and t, you could break it up in terms of its spectrum, if you wish to call it, which would be a function of omega and the spatial frequency. And then if you invoke these inverse transforms, so it would be e to the j omega t from here, and from here it will be e to the minus j kx and then d omega dkx. But what is this one? This guy over here is the electrical engineering way of writing the expression for a forward traveling plane wave, right? In physics, you would write e to the I, and then you would write kx minus omega t, right? But this conforms to the proper electrical engineering convention for a forward traveling wave, right? Makes sense? So that's the reason why I have to write this. Okay, there is no other choice. Goodman does not do that, but I don't care. Okay, I mean he's Goodman. I mean, but if I want to be, consistent, I need to write this. Okay, so you always have to have your own reason, justification, and stick to that. And this is my justification. And of course, you can say that I am not correct, but okay, then you use your own. But this is what I use as my justification for this forward and inverse transform. Is everyone okay with this? All right, similarly, the two-dimensional Fourier transform pair would be just a 2D extension of those. So instead of a single integral, you're going to have double integrals. You'll also have the inverse transform. Instead of 1 over 2 pi, you'll have 1 over 2 pi squared, all right? The other things you should also remember about these Fourier transforms are these simple properties of Fourier transforms. One's called the shift. There are many of them, and you can look them up in any book. But these are the main ones that I remember. One of them is the shift property. So if you have a shift in space, then you add on, as you can see, an extra exponential carrier term, as it is called, in spatial frequency. This is what happens if you scale. Scale means if you make the function bigger, then the transform becomes, you know, narrower in a sense. So that's explained by the scaling property. This is a conjugate property that shows if you have conjugate of x and y, its Fourier transform will be capital F conjugate of invert coordinates. This one is actually important. Remember, Professor Singh was talking about the conjugate image. So this formula is actually important for finding, you know, the conjugate image and, you know, the axis inversion that he was talking about as well. And then this one is another important one, okay? It doesn't really matter if the function is in space or spatial frequency because they are kind of duals of each other. So this is called the interchange property. So if you know the shape of a function in frequency space, then the shape of the function in space would have a similar kind of Fourier transform pair. This is an important property. It's called differentiation. So if you take the derivative of a function with respect to x in spatial frequency, you multiply it by minus j times k sub x, and so on. Okay. Another important property is this convolution. You know, anytime you have convolution of two functions in space, in one domain, say space, for instance, in the other domain, it will correspond to the product of the transform, as you see here. So two important things, there is convolution and something very close to it, it's called correlation, all right? The properties are very much similar. I mean, we'll have to talk a little bit about correlation because we'll probably be talking about optical correlators using, you know, this dynamic holography and also digital holography. So some of these basic properties of convolution and correlation, we need to remember. Okay with this chart here? Any questions? All right, some other, you know, kind of Fourier transforms of some functions. This is actually what I also tell my students. You don't need to remember the, you know, the details. Yes, details are important, but at least you should remember the shapes. So for instance, if someone says what or asks, what is the Fourier transform of a Gaussian? The answer should be a Gaussian, right? Okay, how is that? Fourier transform of a delta function? Okay, a constant, 1. Okay, I will start with 1. Okay, comb function, comb means a periodic sequence of delta functions. Its Fourier transform is also a comb function. Rectangle function, you know, its Fourier transform is a sinc function. So from there, you probably also know triangle function. Triangle would be a sinc squared because triangle can be thought of as a convolution of two rectangle functions. So that's how you can build up your, so to speak, vocabulary of these transforms. By the way, so as you see, Gaussian has the Fourier transform which has the same shape, right? Okay. Comb function, it's kind of really not a function. It's more in mathematics, it's called distribution, right? Because there are limits of some function. Comb function, okay, that also has a comb. Okay. Any other function you can think of that is its own self Fourier transform? So this is the first time I'm using this phrase, self Fourier transformable functions, meaning functions like this, Gaussian, right? The Gaussian, you see, the Gaussian is a function, its Fourier transform is a Gaussian. Okay, with some scaling, you can make them look exactly the same. So can you, or have you seen any other functions that are self Fourier transformable? Another one, of course, is the comb function. Yeah, I mean, anything else? Anything? Yeah. Lorentzian? No, Lorentzian is not the same. Coming close, actually, but not Lorentzian. First of all, one of the things, how about this hint? Okay, what's a more sophisticated form of Gaussian function? I mean, Gaussian is one in like a class of functions, right? What's the more general class to which Gaussian functions belong to? I'm sorry? not binomial, but binomial is totally different than Gaussian. Binomial is more like a polynomial kind of function. But Gauss, yeah, go ahead. Matthew? Bessel, yeah, Bessel is another kind of function, but not Gaussian. And actually, the Fourier transform of Bessel function is not a Bessel function. Okay, but the class of Hermite Gaussian function. Remember Hermite polynomials, right? Like x times e to the minus x squared. That's the first order Hermite Gaussian. So where have you seen Hermite Gaussians? You're all physicsy people, right? Say that again. Say that again, please. In lasers, okay, lasers, yeah, that's one place you would see that. Another place you would see is in quantum mechanics. The simple, yeah, the simple harmonic oscillator, right? Again, in lasers, it is taught in a very roundabout way. I mean, you have probably learned it from Yari's book or some book like that, okay, how the, modes, right, in the laser cavity are defined. But you see, let me tell you this way. So, you know, you have all heard about the simple harmonic oscillator, I take it, being from physics, because the quantum mechanics guys are absolutely fond of talking about it, right? Simple harmonic oscillator. Okay, so simple harmonic oscillator is described by a second order differential equation. Are you okay with that? Okay, I'm not writing the differential equation just because I didn't write it, but that second order differential equation, you can take the Fourier transform of the entire equation. See, if you have a second order equation, second order means there's a second derivative with respect to, say, y. Okay, like d squared y dt squared. Second derivative of that would be, like omega squared times, the transform of y, right? From the differentiation property, right? And then, simple harmonic oscillator, what does it have? It has a quadratic potential. Okay. See, I'm an electrical engineering guy. I'm talking physics. Okay. It has a quadratic potential. Quadratic potential means, it's a term like, t squared or x squared times y. Okay. So if you take the Fourier transform of, say, x squared times y, where y is a function of x, the x squared would bring down the second derivative, right, by this property. Does that make sense? Is everyone with me on that? Why would it do that? Because the differentiation of a function pulls down j times the other variable, okay, in the other domain. Is everyone okay with that? So if you took the second order equation for the simple harmonic oscillator in quantum mechanics, took the Fourier transform, you're going to find it's exactly the same equation. And since one of the solutions of that, okay, happens to be, the Hermite Gaussian, okay, then that means the Hermite Gaussians must also be a class of self-Fourier transformable functions because they're satisfying the set of self-Fourier transformable differential equations. Okay, so again, these things are not written in textbooks. These are ways you have to reason by yourself. So that's another set of self-Fourier transformable functions. Guess what? That's the reason why there are modes of the laser cavity. Because what's happening in the laser cavity? Well, if you are going between, two mirrors, for instance, in the laser cavity, when light goes from, say, the middle, okay, to one of the mirrors comes back, is exactly the same as, light going from the front focal plane of a lens to the back focal plane of a lens, except here, the lens is replaced by the mirror, so the light is reflected back. So again, once again, you have a case of a self-Fourier transformable function. And what is the class of self-Fourier transformable functions? The set of Hermite Gaussian. And the chapter on laser cavities is closed. Okay. I mean, you look at any other book, it goes pages and pages, and I, for the heck of mine, don't understand a thing of what's going on. Because they're going on and on and on and on with so many, symbols, notations, nothing is needed. I mean, the entire theory of laser oscillation is done, as you see, just by chatting in a few lines. Does that make sense? So that's the beauty of Fourier optics. Okay, so keep some of these in mind, okay, because That should be the way you should be thinking. Okay. Right. Another thing to talk about, this is the last chart we'll do before we stop for today, is this business of a linear system. Linear systems are everywhere. Okay. Fourier optics is all based on linear systems, right? Um, first time when I was taught linear system, when I took a graduate class on linear systems, so one guy, this instructor, okay, multiple choice question. So he asked the question, if I write y equals x plus 1, where x is the input, y is the output, does that represent a linear system? How many say yes? It's a simple equation, y, which is the output, equals x plus 1. X is the input. And it's the equation of a straight line, right? So does it represent a linear system? No. Why not? Yeah, so good. Because, the property of linear system is if I provide twice the input, I should get twice the output. So if I change x to 2x, my output is not, agreeing, in proportionality. So therefore, it's not a linear system. Make sense? Okay, so keep that in mind. Even though the equation is linear, it's not a linear system. All right, so here, input is written as, sorry, f sub I, output is FO, all right, except the problem is in optics, sometimes I stands for the image, which is the output, and O stands for the object, which is the input. But I'm sorry about that. But, we are not only talking about, object and image, but correspondingly, the Fourier transforms are capital Fs on both sides. So you probably know that in the frequency domain or in the spatial frequency domain, FO, capital FO is the product of Fi, capital Fi times capital H, where capital H is called the transfer function. And in the inverse domain, the small fo is the convolution of Fi with H, where small h is the impulse response. Okay with this? Now, this is the property of linear systems we just talked about, and then going by some simple, kind of calculations of what's called a linear space invariant system, you can define these so-called impulse responses and transfer functions. So impulse response and transfer function only holds for a linear space invariant, in this case, system. All right. If it were not space invariant, you could not write this h of x, y, and z. You would have to write, x, y, x prime, y prime, and z, because that h would depend upon the locations where the input is applied and the location where the output is measured. But because of this linear invariance, you have x minus x prime, y minus y prime. So that's how you get to just h of x, y, and z. You okay with this concept here? So keep that in mind. Okay, so we will be mainly talking about linear space invariant systems for which we have impulse response, transfer function, and then for propagation, okay, like Fresnel propagation, you have a certain form for this transfer function, which I said is easy to derive. And you have correspondingly the inverse transform, which is the small h of x, y, and z, which is called the impulse response for propagation. And the impulse response convolved with the input gives you the output, which is also called the Fresnel diffraction formula. Okay?
Can we have a small break for tea or?
Yeah, we can. We can have a small break, large break. Maybe what we should do is, why don't we stop here? I was just telling them, because you just came in, I didn't know the schedule. I was telling them that maybe after this slide, we can stop for the day. And I was asking them some questions along the way, but maybe, we can assign some.
Break and then come
Yeah,
back
and we can give some, small,
Assignments.
assignment. Does that sound good? Yeah. You might be tired of this monotonous talk, but let's go and take
So
a
tea
break.
is ready, so come for
Okay.
tea and again.
No, I think you have a fine class of students. Not students, colleagues, actually. I was telling them really, my own background, the history, how to look at things in different ways and how to get to it. And another thing I said is these slides, maybe I'll email them to you and you can distribute them.
So
Since
dear, dear online participants, we are having a break for 10 minutes.
that's
What do
right,
you think?
online
Get
participants.
back,
Yeah,
again, come
Okay,
back
sir.
after.
right, and we can show you what we are having on the picture. That's the most we can do. Oh, I see. Microphone. Then they'll really come to know what we're doing. Hello. So the first example of linear system is just propagation, okay, for going from one plane to another plane. So that's the first thing I'm going to talk about. So the propagation really, you know, accounts for what is called diffraction, right? That's what propagation does. And I just wanted to give a very simple heuristic analysis or argument for why things spread out when there is diffraction, because that's typically what happens, right? Things spread out. So why do things spread out? Well, simple reason, and this was taught to me by my advisor, is so if you have some bunch of particles or photons, if you wish to call it, coming out through an aperture here of size d, then you really cannot say exactly with proper accuracy the transverse location of where exactly every photon is coming out from. The most you can say is that the photon is going to come out somewhere from this width of the aperture, which is d, which also means there is a certain uncertainty in the transverse position of the photon. And if there is an uncertainty in the transverse position of the photon, there has to be also an uncertainty in the transverse momentum of the photon, just by, the simple Heisenberg's uncertainty principle. And because you have an uncertainty in the transverse momentum, you have the spread of the beam. Why? Because there is a certain transverse component to the momentum, but most of the momentum is along the z direction. So if you take the ratio of the uncertainty in the transverse momentum over the z component of the momentum, it's a very simple calculation you see here. What do you find? You find an angle, and that angle you can call the diffraction angle. And that diffraction angle is of the order of lambda over d. And that's a very important parameter which you should remember. Because when you are working in the lab, okay, I mean, it's not always a good idea to start punching numbers in the calculator. Okay, I mean, if someone says, okay, I have a beam this size and a beam this size, which is going to diffract, more as you go to the far field, you should automatically be able to say from here. Same thing happens, say, in the output of a laser diode. Laser diode beam is elliptical, usually, unless you put some correcting lens and so on. So, it's an ellipse, okay? So one side is wider than the other. But in the far field, the ellipticity is just inverted because the side that is thinner coming out diffracts, at a larger diffraction angle than the side that's, fatter coming out. So those are simple things you can figure out from this very simple formula. And you can do in detail, of course, the scalar diffraction theory and transfer function for propagation. So you start, the way to do that, start from the wave equation, get the Helmholtz equation. In the Helmholtz equation, you put the phasor, as it is called, the phasor in terms of the envelope times, the exponential minus j k0z, because that's what the phasor is. And then you put it in, and then you do some calculations. I'm sure you've seen this before. You get what is called the paraxial wave equation. So paraxial wave equation comes from the Helmholtz equation. And solution of the paraxial wave equation gives you the transfer function for propagation. How? Very easy. Just take the Fourier transform of this equation. That's what I was saying. This is, something I did around like 1982, 83. You take the Fourier transform, but take the Fourier transform with respect to x and y. Then you see these second derivatives have become like kx squared and ky squared, right? And so now you have reduced this partial differential equation to an ordinary differential equation, except in the spatial frequency domain. And this very simple differential equation has this kind of solution. So I cheat from there. I find out the solution as this, where the capital H is called the transfer function for propagation. Are you okay with this? Very simple. Okay. And of course, the inverse transform of this guy, okay, would be called the impulse response, just like we saw in the previous chart. The impulse response, if you have a function that looks like a Gaussian, okay, this is a Gaussian, right? Okay, it's a complex Gaussian. There is more, details about it. But remember the little thing we know? Gaussian's transform is Gaussian. That means Gaussian's inverse transform will have the shape of a Gaussian, and that's what this guy is. Okay, so exactly the same. And this is what is called the impulse response for propagation. And so, in the space domain, the output is the convolution between the input as a function of space with the impulse response. So you can solve a diffraction problem either in the spatial frequency domain through taking the Fourier transform and multiplying it with the transfer function, or you can do it in the inverse domain by doing the convolution, which is the Fresnel diffraction formula. Everyone okay with these concepts? You have seen this before? Now, I talked really about the paraxial, transfer function, right? Because I started from the paraxial wave equation. But you can do the same thing if you started from the Helmholtz equation, okay? Helmholtz equation starts with the relationship with the phasor, okay? And then if you took the Fourier transform of that equation, this is what you would get. And from there, you would get, similarly, what is called the non-paraxial transfer function, a non-paraxial transfer function. In many holography books, that non-paraxial transfer function is written with this symbol G. All right. Why? Because the H is taken up for the hologram function. Okay, so you have to be adaptable to changes in this notation. So this G is what is called the non-paraxial, as you can see, transfer function, the G with the hat on the top, and the G, without the hat, okay, is of course the impulse response, right? By the way, in many holography books, it's also written as G with the subscript PSF. Guess what PSF stands for? Point spread function. Okay, why is it called the point spread function? Right, so it shows really how the point has spread. Okay, these guys need to be more imaginative to sell a product. Okay, I would call it something more fancy. I'm sorry? Correct. Yeah, x and y, but it's also a function of z, because that point spread function changes as you travel with distance. Because the point spreads more and more as you travel.
That is the propagation.
Right, that is the propagation distance. So you can have, depending on what you want, if you want to be approximate, you can use the paraxial transfer function. If you want to be more exact, you can use the non-paraxial transfer function. Okay, non-paraxial transfer function, of course, is more exact because, it takes care better of evanescent waves. So that's something you should keep in mind. But otherwise, okay, I mean, either one will work, or you can just simply use the impulse response, as it is called, which actually is the inverse transform of this, and in fact does work out to be exactly this guy. And as you know, this guy is really the expression for a diverging spherical wave, as it should be, right? The one thing I would like to point out is relevance of the angular plane wave spectrum is very important, the angular plane wave spectrum approach, because every optical field can be thought of as broken up into a set of, as you see here, traveling waves, okay, traveling in different directions. So this spectrum, that is just the Fourier transform of this thing, is really the amplitude of that plane wave that is traveling along a certain direction, given by these, spatial frequencies, kx, ky, and of course kz. Here, of course, the assumption is, okay, the kz is approximately k0 because the angles are small. Okay. But is this clear to everyone? So this is really the relevance of the angular plane wave spectrum. So, any arbitrary profile can be broken up once illuminated, okay, by an optical field. That optical field can be always expressed in terms of this angular plane wave spectrum. That means it can be decomposed into different plane waves of these amplitudes traveling in different directions. And you can exactly solve the problem by actually geometrically figuring out how much distance is traveled to the next optical element, and then comparing the distances between different spectral components, adding them up, of course, properly, and that gives you the final, optical field. So one way to, decompose, so to speak, an arbitrary optical field is through the angular plane wave spectrum, right? There's another way, okay? So what have we done here? Here we have decomposed this arbitrary electric field into a bunch of plane waves going on. You can also decompose it into a bunch of spherical waves going on, okay? That means you can take every point on this, arbitrary field as a point source, and you can, theoretically, you can propagate each one of those point sources by different distances. You know how a point source would go, just spherical waves, and then add everything up. So that's your composite field. That's another way to do the problem. In fact, that way is called the point cloud method in holography. Okay, so keep that in mind. Now, that is a very easy thing to do. So sometimes now what some people do, because there are millions and millions of calculations now you need to do. So now what some people also do is take a bunch of point clouds on one plane, okay, another bunch of point clouds on another plane, and then break up the entire 3D space into a bunch of discrete layers, each layer having a set of point clouds, and then propagate them. Okay. So on this note, okay, there's linear systems more here. Another example of linear systems that someone was asking is the single lens and double lens system, but we can talk about that tomorrow. But what I was thinking is, in order to maybe just stimulate your, interest, appetite, whichever one you want to call it, with the Fourier transforms and at least the propagation part, because this is something you need to know. I was going to suggest, this is what I was going to suggest. So I don't know how should I give out these problems to students, but this is the general nature of the problem. So this is what I want you to do, or at least start. Okay, you don't have to finish it tomorrow. You don't have to finish it tomorrow. Okay, so this was an exam that I gave my Fourier optics students, as you see, just a week ago. All right, what is it? Okay, you know about the transfer function. So okay, so take the Gaussian beam. This is a Gaussian beam, simple Gaussian beam, okay, and just use the transfer function for propagation. One transverse dimension is enough. One transverse dimension is enough. And just, plot it, okay? Just plot, how the Gaussian beam looks like after it's traveled, some distance. And how much distance, okay? I've given you the distance, say, like the Rayleigh distance. Every Gaussian beam, has a Rayleigh range. and the width of the Gaussian beam is given, like 10 microns, okay? Wavelength is given, 1 micron here. So all numbers are very simple. So what I want you to do is first, number one, plot this initial Gaussian beam, okay? Use any plotting routine, okay? Plot the initial Gaussian beam. Second, okay, take this Gaussian beam. This will take you some time, but okay, but you need to do it eventually, not tomorrow, but you should get started and we'll discuss more. So take this Gaussian, take its Fourier transform. All right. Now, Fourier transform doesn't mean just pushing a button. No, it doesn't work that way. You have to sample the function. Okay, you have to sample the function. So you have, maybe a 1024 point FFT to sample the function. But when you sample the function, you should also be careful what is the, sample size and so on, or the delta x, so to speak. Is everyone understanding what I'm saying? So, you're sampling in discrete space. Okay, so you're getting 1024 samples. The 1024 samples you're centering, say at x equals 0. Then on one side, okay, if you have 1024 samples, on one side you will go to 512, other side you will go to 511. Why? Because the middle one also counts as 1. You okay with this? So you plot this, okay, but then you have to be careful how wide you choose your delta x, because, that will show how wide your Gaussian function looks like. All right, so what's the issue with this width of the Gaussian in the space domain? Now what you're going to do, you're going to push the FFT button. When you push the FFT button, out will come a set of 1024 numbers. Okay, because you put in 1024 numbers, the computer is stupid, it gives you 1024 numbers. What do you make of the numbers? Well, it's a spectrum, of course, but you should make sure the spectrum is such that it looks like a Gaussian. Make sense? But when you do this on the computer, if your function was centered at, like at x equals 0 to start with, the spectrum will not be centered at x equals 0. The spectrum will be split up. So, and you can check that out by yourself, okay? So if you start out with a function which is, I don't know, there is no whiteboard over here.
Yeah.
Oh, it is there? Well, but the online guys will not be able to see it. That's fine. I'm going to draw something. Yeah, the online guys are not going to be able to see it. I guess. But okay, let me see if I can. What's the best way to show it? That's what I'm trying to say. If I can take out another. Sorry, I want to actually open another PowerPoint. Is this actually shown on the screen now? Okay. All right. All right. So let me attempt to draw. Okay. So let me attempt to draw. So all I'm saying is, if in the space domain I had and instead of a Gaussian, I'm just going to draw a triangle. That's okay because it looks kind of like Gaussian. So so if I have a triangle function like this. Are you okay here with me with this diagram? So this is your center at 0, and then this is like your Gaussian function, right? Your Gaussian function. You take what you want, okay? I mean, you have your choice, okay? You have a Gaussian function width or waist of what was it, 10 micron. You space it however you want on this axis, okay? You choose a certain delta x, but I would say, as a rule of thumb, make sure that the width of the Gaussian is contained to within, like I would say, 20% to 30% of this entire interval. That's a good number to have. And you'll see when you take the Fourier transform of this, okay, if you take the Fourier transform, then the Fourier transform is going to look like this. So if you take the Fourier transform, okay, if you take the Fourier transform will not look centered like so. So what will happen to the Fourier transform? Well, the Fourier transform is gonna look like this. This Fourier transform, of course, looks also like a Gaussian, right? But the Gaussian is gonna look like this. I don't know how to center that way. I don't know what I can do. So right here. So the Fourier transform is gonna look like this. Okay? The Fourier transform is gonna look like that. So, you narrower you make it here, what's going to happen here is going to become wider, right? So you need to be able to figure out what is your sampling interval that you want. Typically here, you see, if you have a sampling interval, say delta x, okay? If you have sampling interval delta x, so then this total width is n times delta x, right? It's n times delta x, and 2 pi divided by that n times delta x will be the resolution in the frequency domain. Okay. So anyways, you work on it just up to this part. Try to see how the spectrum of the Gaussian looks like, right? And then what you need to do is, if that is the case, then the next thing you need to do is what is called a FFT shift. FFT shift brings the spectrum centered here. So that means this part is moved by half a period, this part is moved by half a period. So then the spectrum is centered right here. Why would you like to do that? Because next step you want to multiply it with the transfer function for propagation. And then as you multiply it with the transfer function, you're going to see how the spectrum changes. So we'll talk more about that in the next class. But this will be the first step to do. Okay. Then get up to the Fourier transform. And what I would suggest is, so I don't know how I should distribute that problem to all
You
the
can
students.
send me that email.
Okay, then I'll send you this entire set, okay? Because that will be useful. We'll do it step by step. So this problem, I'll tell you why I give this problem. I always give the problem starting out with the Gaussian. Why? Because I know the answer, right? That's number one. You always want to check with some things you know. So this Gaussian, you can see how it propagates, right? And then another thing you can do in this particular case, I had asked the students, you don't need to do that, but I asked them to plot the width. How do you find the width of a Gaussian? You take the maximum value, you write a short program to find the 1 over e point, and then you find the distance between the 1 over e point. So that's how you find the width of the Gaussian. And you know how the Gaussian's width is going to change, right? All of you, I understand, have known the laser class, or even here, okay? I mean, it's just expanding according to the little formula, W square equals W0 square times 1 plus Z over ZR square, that's it. Okay, now you could also do the same thing for a super Gaussian. And this is again something I always tell my students to do. Going from a Gaussian to, what's a super Gaussian? A Gaussian where this argument is raised instead of power 2 to the power of 4, 5, 6, whatever. What do you gain by doing that? The function becomes sharper. Okay, the function becomes sharper and sharper. What's the advantage of that? In the limit, it will look like a rectangle function, right? So, if you take its Fourier transform, what should it look like? Same function. So again, you know the answer, right? So that's the advantage of going like this. And in fact, when I myself program or try to program, a square wave, I always write a super Gaussian. Super Gaussian to a power of, like 8 or so is good enough approximation for a square wave. Or even a circle, okay? For a circle function, I would write, x squared plus y squared to the power of maybe 8 or something like that, or power of 4, I guess. Are you okay with this? So if you can work on that, that will at least give you an idea. And was another good thing here. So once we go through this problem, so your Gaussian, let's suppose, is propagating, right? It's propagating some distance, okay? Say ZR. Now you can also introduce, say for instance, a reference beam, because we are doing holography, right? We can put a reference beam coming in at an angle or zero, whatever you want to do, because it's all numerical. So let it come in at an angle, okay? If you come in at an angle, then you're registering what? Off-axis hologram, like the Michigan guy, like light and open night. So you can register that hologram, okay, on the computer. So what have you done? You've really done a computer-generated hologram. But why are you doing it? Because, we are cheap. We want to do this course and trying to understand how we can, record a digital hologram and how we can reconstruct. So the recording part also we are doing on the computer, but in the process, we're also learning about how computer-generated holograms are done. Right? So once we record it, what are we going to do after that? Well, we are going to try to separate, those parts, remember, because, otherwise they will have the twin image problem. So we'll try to separate the parts. How? By taking its Fourier transform and then cropping some part. And then again, propagating, either forward propagating or backward propagating, depends on which one we crop, to get the virtual image or the real image. Real image is also called the, conjugate image, as, you heard Professor Singh talk about. So I think just playing around with this Gaussian is going to give you a good exercise of what happens. And not only Gaussian, then you can go to the square wave, and let's see how far we go with it. Does this sound like a good plan here? And the best part of this is you know all the answers, right? All right. I'm gonna then email you, right? And how do I email you? Huh? Wi-Fi is working here.
Admin, sir.
Okay.
Admin password name, Wi-Fi name admin.
Oh, you can give me, yeah. So I think it's connected to Wi-Fi. Maybe it's connected. No, I need to get out of all of this, but then I need to get to my email.
But I have solved the Wi-Fi problem.
This email, oh,
Temporary login and password.
okay. I don't know how I got it, because I needed to log in using the 2FA. Oh, well. Yeah, okay. But let me see if it goes, all right? I mean, that's enough.
Yes, left. Yes, going for the oh, you have to return. I thought that you will return after it's right for the 6. Then come and stay for a day or two. Some other then come and do your activity. No, he will be online. He can be in traveling. He has to again travel first. He has requested to talk on everything more. So yeah, after tomorrow. Start the talk at 9:30 or 10. That okay. Then we will.
Okay, I
Or
think
else,
it's you.
what you can do, I can request him, he can give the talk and you can attend from online at home in the hostel itself. Or you come here. Then we have to start. Next lecture from 10:30. The range is talk from 9:30 to 10:30.
Or tomorrow?
No, not tomorrow. Yeah.
Oh, there.
Every day I have scheduled
Yeah, someone else, right?
10:30.
Okay.
You
That's-
talk from 10:30.
Okay.
There is two speakers.
Yeah,
They
yeah.
have requested for
Right.
a morning class.
Okay.
So one will be talking from USA, so he's in
Oh,
the,
that's right, the one from Caltech.
no, Stanford.
Stanford, yeah, okay.
He will be lecture in the morning.